J.
J is what?
Just J is the current carried by moving electrons.
Oh, okay, right.
So it's J, it's got three indices, so we call it X, Y, Z if you like, or we call it J, I'll call it JI, J in the ith direction. That's the current carried by electrons. But then you have a current which is carried by electromagnetism, so such things as d by dt. So this is current 1. So this is current. That's current 1. Then current 2. Current 2 is carried by, for example, electromagnetic fields, and another that will be tertiary partial d by dt. So a rate of change of electric field carries a current, but also the curl of B carries a current, and it absolutely carries a current. If B is curling, current is being transmitted somewhere. It can be a long way away at the speed of light, and that's how radio transmission works. For example, we have something which is light here, and then you sort of get hello mum, but the currents come through the ether or come through empty space. That's d by t. That's current 2. But then you have current 3. In fact, there are more forms of current. And current 3, or current, these are really current densities. These are really densities. So you should think about them as being intensive quantities. Of course, they get low down by the electron. But current 3 is a quantum mechanical current. So you write a quantum mechanical current as phi grad psi star minus psi star grad psi. So what you do is you have some wave function, the wave function like a to the I kx minus omega t. It's some complex quantum mechanical wave function. You look at the spatial rate of change of that, multiply it by one thing, and then subtract the complex conjugate of that, so it's like a commutator of those things over conjugation, over differentiation. And that's a current. And that's a current that a single electron can carry. So 25 years ago I went, as the first one, to really go into the single electron regime with single electron pumps and single electron systems. So at that stage you carry current of less than one electron. And then the next level down, so there is a level below this, and that's to add the current into a coherent EM charge thing. So that's to draw current where we're looking at a Laughlin current at a fractional quantum Hall regime current, at a fractional charge current. So that's the next level down, that's the next level we want to get to for these things. So you can do electrons on less than one electron. We can do multiple information on just one electron.
Now, currently, which is the current that powers my computer here?
The current that powers the thing that powers your computer there is electromagnetic. So it's number 2.
And how is it flowing through the wires?
It's not flowing through the wires, it's flowing around the wires.
Around the wires.
As according to Feynman, so if you look at Feynman, the energy is being transmitted through the current, through the field. Yes. So it's a charge density wave. So what's happening is the electrons are actually moving in. Well, they are actually moving in, but of course it's not a DC current, they're going in and out. So you've got an AC. Well, that's DC coming in. Sorry, where do you want me to tell you where it is? If it's there, it's no. Well, okay, it's coming through. It's coming through a charge density wave in the AC stuff.
Can I read about this? I can't find it anywhere in the literature. Is this in your mind, or is this?
Oh, you can. You just need to go to very advanced literature. So this stuff is, for example, an iceberg. Iceberg's written quantum mechanics. A decent quantum mechanics textbook that actually does the details. That's in Feynman, lectures in physics, saying that the energy in the wire is transmitted outside the wire. I mean, this stuff's in chemistry books and schools. This is school shit level. That's a second year electromagnetism. That's third year quantum mechanics. I'm talking about Scotland, where we have 4 years. Third year or fourth year final year quantum mechanics.
So how are you scaling your qubits or your electron?
Pardon?
How are you scaling your qubits or your electron?
I'm not scaling the qubits, I don't do that shit.
So you just said one qubit does the whole thing?
No, I said one electron does the whole thing.
One electron could
one
have
electron.
any number of qubits.
One electron can contain information in space, is what I'm saying.
Well,
so that's far smaller than a qubit.
But you're not doing the whole thing just on one electron.
No, I'm not doing the whole thing on one electron at the moment. I'm saying that one could, in principle, do that. The next generation of electronics will do that.
And can I just ask current number 2? Is this the one that I sort of more can understand?
It's basically current electromagnetism.
Which is basically number 2, you said it's what's flowing in one vacuum around my conductor. conductors.
Yes.
Now, what concentrates around the conductors?
Concentrates around the conductors. It's because it is of the
It breaks down,
cooperative
isn't it?
state of the electron, proton,
It breaks
neutron
down, isn't it?
conducting
Electrons
system.
to weight particles.
So what you have is you have
So why don't we define a
Hold on, you can do that for the next generation.
voltage and current are two
I'll show you
different
more.
things.
One electron,
So how do you get the voltage?
I'll show you
Okay,
more.
voltage and current. So what a voltage is the energy per charge,
Yes.
and what a current is the number of charges per second. Right. So you can have what you have is you have a quantized conductance. So the conductance is limited in the quantization of the number of electrons carrying it. So those electrons can be at a specific energy. So I published a paper in 1989 on looking at the voltage carried, at the energy carried, hot electron spectroscopy with quantum yes, hot electron spectroscopy with quantum point contact. So what you do is you take single electrons, eject them one at a time above the Fermi level, coherently. So you stick them at an energy which is above so you have an energy of C of electrons just sitting there, and you stick electrons in at a higher energy, but they don't scatter, so they stay at that energy for some time, and then do spectroscopy with them. So what those things have is they carry a current, which is just a charge, which is actually just a single charge in motion, flying through an empty, looks like a vacuum. So the current is not defined because it's basically a number of charges per second, so at that stage. But that electron is spread out because in the solid state systems we were using electron wavelength was about 14 nanometers, so you've got to imagine a quantum mechanical wave, which is an exponential wave. So you've got a wave, and that wave is sitting at an energy where the state's completely free below it. So you have a voltage above the Fermi level, and you have a Fermi velocity which you're sitting at, which is enhanced by the voltage which you're in. So the thing's flying at about 10 to the 6 meters per second. It's doing about 1,000 kilometers a second in a solid state. So then you have a single electron, which is the first current,
There you go.
carrying something which is associated with the third
No, I
current.
think the first current. I don't believe in the first current. The first current is only part of
Seen
the
it?
accelerator.
Something similar.
I agree.
That.
You and I both. Yeah.
The second current, let's just take a coax cable.
The block's made out of water and it's bouncing on water, it's going on.
There's a transverse wave going across the coax.
Careful and the waves.
Now let's take it on. Now we've got a transfer which in the transverse counts that way.
Stick a pin in it, that pops your electron.
Transmitting DC, not AC. So I've got this path going through, and I terminate this.
And another pulse going through.
And another path, I've got a step going through initially.
Yes, so you've got the frequency AC signal as you're saying.
And then I got this.
Yes. How does that travel? Travels as a pulse and an electromagnetic pulse through the system. How do you know? Proof.
I know it's a transverse wave.
It's a transverse wave at 2/3 the speed of light.
No, it's 2/3 or it's...
No, it's 2/3 of the sound. Standard coax
It's
is 2/3.
2/3 of the...
Depends on the control. Air core is nearly the speed of light.
Okay.
Air core cable, if the beam is about to it's the speed of light. Yes, exactly. Yeah. So an air core cable is the speed of light and electromagnetic.
What time's finished?
Because it's an experiment to charge
We used it.
Let me show you what they got.
coax through a huge resistor.
Through a what? Resistor?
You have an open coax.
1936.
So an air core coax, yes. An air core coax.
Where are you standing?
No, there you go.
Oh, yeah, I'm right next door.
50 over 2/3 speed of light, yeah, roughly.
Oh, what's that like?
It's like an 85-year-old woman, she's got a free will, and most of the time,
Yes.
she's supposed to be nice and British, right? That's fun.
Yeah.
How much does it cost to do that?
Yeah, okay.
I think, I was supposed to bring my wife, so I've got twice in a room, but I think it was one of, it's like, it was 60, 50, or that's
And then, well, when you charge it, it goes around here, it goes to 5 volts. And it's only if you
I don't mind paying a bit more for a bit of comfort.
They actually got the one house coming up and then the 18 line back.
That's right, exactly. And then it drops again in the second reflection.
No, the even before I think it's 75 and then
You terminate it so it doesn't reflect, it just dies with the
the other end it reflects once.
Yes.
She may not want to do it anymore. So
Yes, you can use it as a positive.
Oh, well,
Yeah,
it's nice to see that.
twice that. Yeah, that's right.
So which shows that it's a transverse wave out. So
It's not really. Is it transverse? Look, it's
the front of the front is the transverse wave. You know, what's behind it? This is what I'm asking you. What's behind it? You know, the
what's behind it is, well, what's behind it mathematically are Maxwell's equations.
Yeah,
what's
behind
behind it
it
physically?
physically, what I mean,
What's behind it physically is the energy stored in the electric field, or electromagnetic field. So what you've done is you've charged it up. You've charged up it's not a capacitor because it's a travelling wave. But what you've done is you've charged up a physical system.
Yeah, but isn't, okay, that's the next step. There isn't a capacitor.
Yeah. It's not a capacitor, it's an inductor. It's
Isn't
an inductor.
isn't a capacitor a completely misting coax cable, and you have basically these things going up and down, up and down, up and down, up and down all the time.
The difference between a capacitor and the way you use a coax cable, because a coax cable is a resistor-inductor, is a capacitor-inductor.
Completely,
Yeah.
but it is, if I
Transmission line. Capacitor.
yes, I know it's a transmission line. If you take if I charge a coax cable up to 10 volts, the energy in that coax cable is half CV squared.
Correct.
Okay.
And when you let go of it, the reason it goes to half is because half.
Yes, I fully understand that.
Exactly.
I
Exactly.
can.
Yes, sir.
I can now. There is one guy who says when it's charged out, he sees this as a wave taking up and down. You know, lots of waves doing this, and you know, he says
You can see it how we like, but it is what it is.
yeah, no, but what he says, the capacitor is very much the same. You basically, although it's mistuned, you put a pulse into the center. You know, instead of being a wave you put down the plane, this pulse is going out incrementally all along, reflecting on the back, coming back. As soon as it hits coming back, it steps up. And this is interesting. You take a coax cable and watch it, the potential of it rise after you put it up at 1 mega ohm. You get a nice step function like this, which it follows the exponential curve. Now, on the capacitor, you can't see these little steps anymore because it's only that short and they go in all directions, so that smooths out into the, you know, this is what one particular person says. But
No, I think there's a big deal of truth in that because we both talk about energy stored in what's an electromagnetic field. And once you start changing the electromagnetic environment, you get an electromagnetic system. So that's why you get a factor of 2 drop, because half of it goes into magnetic.
anyway, my mouse started working and I must stop working again. It works on the Apple side, it doesn't work on the Windows side of my Apple.
What are you trying to work?
I'm trying to, well, I need to do some work, but my mouse is